So these drones, we control them wirelessly, right? And it's not just the control, it's also the video feed. All right, we have two things going on. We're sending signal from our controller to the drone, and we're also receiving video from the VTX to our goggles. Okay, so we have two main wireless things going on. Okay, in order to talk wireless transmissions, we need to understand frequency and wavelength. Okay, so electromagnetic radiation is all around us. Okay, uh, of course, you probably know of X-ray, which is generally you see as like, oh, it's dangerous. But it's because it's a high energy form of radiation. Okay. And that can cause atomic level damage. Okay. But do you know that visible light is also radiation? Okay. So it's just something that we can see. We can't see a bunch of other stuff. I can't see Wi-Fi signals. I can't see, I can't see the X-ray, but visible light specifically in the range between about, you guys taking like a multispectral class anyway? You guys yet? Okay. But those sensors can see things beyond what we can see. Is our human vision, I believe it's like between 400 and 600 nanometers. Okay. But before I start throwing out random numbers, let me explain. So wavelength, what happens is uh, the radiation travels in a wave. Okay. And the wavelength is from one point to the next point of that same spot. So you can either measure from the peak to here. So the distance between this peak and this peak, that's one wavelength, and you literally measure the length. Okay, so that's why you see here it's in meters. And we have all of our prefixes. So kilometer is bigger than a meter, which is bigger than a centimeter. Then it goes to millimeter, nanometer, so on and so forth. So you see the drastic difference. One wavelength, 6,000 kilometers versus we get down here to X-rays, nanometers. Nanometer is, I believe, a millionth of a meter. Yeah. So yeah, it's such a drastic difference. So we have the actual wave. Oh, I just realized this is misspelled. Okay. We have the actual wavelength itself. And then we have the frequency, which is how fast something happens per second, represented by the unit hertz. So hertz is just the equivalent of 1/2 seconds. How many times something happens per second? Okay. So the wavelength is the distance, hertz is how often that's happening. All right. Do you guys notice something the relationship between wavelength and frequency?
They're inversely proportional.
Correct. So let's take a look here. This is a huge wavelength, right? What about the frequency? It's pretty low. It's just a hertz. Now it's a mega. A mega is a millionth. And then we go to giga. That's a billionth. And then we go to tera. So you can see, but then look at this. This is let's say 3 centimeters. 3 centimeters is like this big, okay? And this is 10 gigahertz, much bigger than 50 gigahertz. So it's an inverse relationship. As one gets bigger, the other gets smaller. All right. Okay, now let's take a look here. You're gonna see that the info that we have right here is going to be displayed in our frequency. But I usually remember, but you can find what the other one is through a formula that I will show. But let me see, visible light wavelength. It should be about 4 to 600 something. Yeah, 4 to 700 nanometers. Okay, so that's the visible spectrum that we can see. But this is just our very narrow observable electromagnetic radiation. When it becomes, as we go to the left, the wavelength gets longer, and so the smallest wavelength of our visible light is red. Okay, you can see right here. All right, so not smallest, the longest. The longest you can see right here. It's 700. And then when you go beyond 700, it becomes infrared. Infrared, actually, a lot of times you feel that as heat. Okay, you may not see it, but you experience it as heat. And actually, infrared is what we have in your basic remote control. You guys know that? Let me see if I can find a remote control. I know there's one in there. Let's see. You got a remote? I'm talking like those TV remote controls. Thought there was one at the TV. Yeah. Okay.
Yeah, that little red print at the top with the remote.
Yeah, so you don't see it here, but you see like a little window.
Yeah.
I need a steel battery from this real quick. Okay, so if I point this to you right now, you don't see anything, right? Okay. Let me see. Oh. Oh, you see that? Yeah, so this is infrared light. So cameras have a like a wider spectrum than our own eyes. So this is to show you this works. It's just that our eyes can't pick up this wavelength, okay? So this is beyond our visible light, and then this is right here. That's why we have a remote control right here.
Well, that's why it's left of it, because it's below the red we can see.
Yeah. So the red is right here. The red is the longest wavelength we can still visibly see. And then infrared, which is this thing, is right here. It falls off of the spectrum. Okay. On the other hand, violet is the shortest wavelength. And after that, we have UV, right? We don't see the UV from the sun, but we know exists because you get sunburn, right? So, yeah, so that's that's an example that of it exists. We just don't know, or we just don't see it. Okay, so you can see as we go left, it becomes longer wavelength, and here's some examples of that. Okay, yes, question.
So 1 hertz is always going to be equivalent to 300 meters.
About, yes, no, it is. It is a fixed relationship, and actually, this is a. Before I move on, the next slide is actually going to explain how you know. Any questions on how this works? Okay. We have a simple formula right here that relates the frequency and the wavelength. Remember how we said that wavelength and frequency are inversely proportional? You see it's on the same side of the equation. C is the speed of light. It's a constant. That is a property of the universe, okay? It's always going to be 3 times 10 to the 8 meters per second squared. Incredibly fast, incredibly fast. So I think if you were to like, assuming you can have the light go around the world, I think it'll just take a couple seconds to literally just go around the entire world. Let me see. I want to know now. Speed, how long for light to go around the world? Oh,
Yeah.
I'm sorry, even less. Okay. I'm sorry, even less. 0.13 seconds. Okay, that's how fast the light is. Okay.
Just 1 second.
Yeah. So you guys know like planets, they measure by light years. How many years it takes for light to travel. So a lot of times you see the stars, it may be dead already, but the light is still on its way to us. Okay. That just gives you an idea how far they really are. Because if it only takes 0.13 seconds for light to go around the Earth, which is already huge, right? You guys gone on a plane across the world. Yeah, like and planes are still traveling well subsonic, so but still like 500, 600 miles an hour, very fast. Can you imagine how far that is? Okay, but just to put things into reference, yeah, the speed of light, it's a constant. Right here, I and R are inverse, or yeah, they're inverse relationship, right? So I don't know if you guys noticed if you practiced enough leading up to the exam, as you, let's say you fix V, let's say you fix V, and this is 12. Instead of R being 6, let's say R is now 4. What does I have to be?
3.
Yeah, 3. So notice R went from 6 to 4. It went down. And previously it was 2. Now it went up to 3. Okay, so that's what I mean by inverse relationship. So you can see right here, if they're on the same side of the equation, if you reduce one, the other has to increase in order to equal C. That's the whole point of an inverse relationship. Okay, so to your point, yes. When you know one, so let's say you were saying, what were you saying earlier?
1 hertz.
1 hertz. Okay, so one hertz is, well, it's off the chart because 1 hertz is like down here. Are you talking 1 gigahertz or 1 megahertz? Okay, so 1 megahertz is basically going to always be 300 meters. That's not really going to change because of the equation I was talking about earlier. Okay. Yeah, so this is a fixed thing. Unless in the future the speed of light changes. But no, that's a fixed property. Gravity, on the other hand, can change on our because it's tied to our physical mass of the Earth. But I don't think in many lifetimes we will notice. Yeah. But the speed of light, that's just like a universal principle. Okay. E equals MC squared, you guys. That's what the C stands for. The C. Yeah. Energy equals mass, speed of light squared. Yeah. Anyways, we're not here for physics, so let's continue on. All right, so we're gonna focus on a couple of different. In this case, I'm using frequency, but I guess you can also equate that to wavelength. But oftentimes, we will use the frequency to describe the type of wireless uh, wireless communication we're using here. Okay, right? We could write it into wavelength, but frequency is kind of the standard here. Okay, so FCC, you guys know FCC? Federal Communications Commission. All right, they are like the FAA, but for radio communications. Okay, so they have designated specific, just like FAA, they designate different class airspace. Okay, FCC has designated specific frequencies for particular use cases. Okay, so a lot of them have been sectioned off. This one's for radio, FM radio. This one's for AM radio. This is for emergency communications. This one's for television, whatever. There are a couple, those are license frequencies. You need to apply for a license and like reserve that slot, okay? Because they don't want people, there's only so many frequencies available. They don't want people like crowding over it. There's a couple of free-for-alls, the equivalent of your class golf, okay, which is 2.4 gigahertz, 915 megahertz, and 5.8 gigahertz. Okay, those are your unlicensed frequency, meaning anyone can use it. Do you guys have a ham radio license? You don't need one to use your phone, right? Because we're using unlicensed frequency. As a result, though, very crowded. A lot of devices are using these frequencies. It's not to say they're exactly on 2.40000. It's a window. It's like 2.3 to like 2.5. So you can have a device on like 2.351 and then 2.362 and it'll be okay. I mean, it'll be okay assuming other factors are also considered in terms of like power outage and your bandwidth and things like that. But yeah, so 2.4, this one's very common for Wi-Fi. In fact, you might have seen this if you go to someone's house and they have a 2.4 and a 5.8. gigahertz. Okay. So that's very common. And then 5.8 is another common one. 5.8 is a higher frequency. Okay. That means you can handle higher data rates. You're constantly sending things faster. Okay. So that's why, particularly, we use the 5.8 more for our VTX, our video, and the 2.4 for the controller. Because which one sends more data? Yeah, the video is like sending a lot more data than just a couple of simple bits. Did you have something?
I think for like the Rush Tank Solo VTX, it actually says on the back of it, you have to have a ham radio license to
Okay.
operate it.
So
So
it's very possible because it's not just frequency you have to consider, it's also the power output.
yeah, they
Yeah.
have to, they're way past the.
Right. Because you can be in a unlicensed frequency, but if you crank up the power, which is like the equivalent of yelling louder, you're gonna drown out other people. And that's where, yeah, now you're gonna have to, there's multiple conditions that can trigger you needing a license. You go outside, you go into a license frequency, you need a ham radio license. You have too much power, you need a ham radio license. So that's probably why. I think it's based off power more than the
Yeah,
frequency.
it's like, I know for that one, I think it's labeled on there, cause obviously you can control your power,
Yeah.
but it's rated to go way above.
Okay, so
You'll blast everybody.
right. So assuming you stay, I don't know actually what, I gotta look up the limit. But assuming you stay in a lower power, you don't need a
I assume so,
license.
but-
Yeah. What is the power limit for unlicensed frequency?
Ham radio license. Well,
Yeah, yeah, it's a good thing to have. It's like also you take a little test and stuff. Does anyone have it?
Homework.
You're working on it? Okay. It shouldn't be too bad, I assume, right? Okay.
This is half the stuff we've gone over is like what I'm missing.
What? Like just from now?
Yeah,
Oh, really?
this is like the main stuff, and then what we've kind of been going over is like even the power board that we worked on.
Oh, this thing right here?
Yeah,
Oh, you need to know this
Yeah.
stuff? Really?
it
Okay.
asks like, it gives you like a diagram, and it's like, what is this symbol? And
Oh,
the first time I was getting it wrong, because I didn't know what the symbol for
Oh,
resistor was.
okay. Yeah.
So it's like basic
Okay,
stuff, but what
okay.
we're talking about now is.
Oh, that's good. Maybe you guys are all almost ready to take the ham radio license. Yeah. Yeah. I actually thought about getting it. I just like I haven't had to, but like yeah, maybe I'll get
I
it.
think it's good for like 10 years too.
Okay.
Oh, that's
Okay.
worth it. Yeah.
Remix class.
Yeah, like yeah, exactly. Yeah. Yeah. So it looks like right here the limitation if without needing a ham radio license is 1 watt. So there you go.
Which is plenty of power for.
Yeah.
VTX would probably.
Yeah, well, this is what I was just talking about. 2.4, 5.8, 9, 15. Okay. Now, the drawback of 5.8, because 5.8 seems great, doesn't it? It has higher data rates. The drawback is, well, what's the difference between 5.8 and 2.4? It's a higher frequency, but
Shorter wavelength.
shorter wavelength. Okay. It cannot go as far. Okay, so this is where the benefit of a 915 is. The 915 is the lowest frequency, but it's the longest wavelength. So it's good for distance and signal penetration. Okay. So but there is a disadvantage. You need bigger antennas. Yeah. So you've seen like those what is a big radio tower? No, that's transmission. But anyways, you need a bigger antenna. So that's what it is. Okay. Question, yes.
This, I guess, as it applies to drones. So like if you were to take a whole bunch of drones. and
Yeah.
You got a job in Europe.
Yeah.
Are you gonna show up and things are gonna start acting weird because they're not under this same provision for frequency?
Oh, you might just violate their like open frequency thing. So that's why like when you buy a device, I don't know if you notice, you have an FCC option and then they have whatever EU option that they use over there. Because I don't know what their Now I have to look it up. What is the EU unlicensed frequencies? Because it's different from us, I would assume. Okay, actually, it looks like they have very
I
similar.
was gonna say, cause when you get your ham radio, there's 3 levels to it, and
Yeah.
once you get the level 3, which I'm forgetting what it is, it allows you to communicate worldwide.
Okay, that would make sense because like imagine like Apple designed a phone and it's using like unlicensed frequency and you go to another country and now it's like, oh, you're violating that. So it's I guess it makes sense that things are somewhat standardized. Yeah. But I think the EU is more strict in terms of power output. I think they don't allow as high. Is that what you're gonna say?
So a while ago, back in my school, I had to build a drone. but
Yeah.
They had us get this special chip that was only US because of the frequency it was outputting.
Yeah.
Because it was on a certain spectrum. Because if we got the European one, it would be illegal to use
Yeah.
in the US. So
Right. So you just have to check. Yeah, if you're gonna try to use something like this in yeah, see, look, they're limiting you a lot more. We said 1 watt, right? It looks like they have higher limitation or a bigger limitation, which generally that's what it is. The EU has like a tighter, I feel like they have tighter restrictions. Sometimes in a good way, yeah. Apparently, like their fast food is like healthier than what we have here.
Yeah, it's a better portion there.
Yeah. Yeah, so you feel less guilty going to McDonald's, I guess, in Germany or whatever. Yeah. Yeah, a little less guilty. But they are the reason we have USB-C on the Apple products. You guys know that? Yeah.
Apple was easy.
Yeah. So actually, I'm for that. I'm glad that happened.
They said to do that for the Nintendo Switch too. They have to release.
Oh,
a model
really?
that has a changeable battery.
Yeah.
Because now,
Oh,
like,
yeah.
exactly.
I
And
saw
and a bunch of people are buying new ones now.
Yeah.
they're not gonna do it because they lose money that way and they don't want people to pass.
Oh, this is what I want to show. FCC band like spectrum band allocation chart. There it is. Okay. So this is a visualization. Oh my gosh, this is like it's okay, so I'll zoom in because it's gonna be too much to look at from this distance. Oh, I have to okay, here it is. Okay, sorry, it's a little
Yeah, this chart's all.
I had to click on a PDF to open another PDF. Great. You see, like this is a PDF. I click on it to open another PDF. Okay, great. Okay, so you can see right here, this chart shows from 0 kilohertz down to whatever this is, 300 gigahertz. Okay, and let's just zoom in on some random one. You see space research. Okay, space research, this has been allocated out.
Earth exploration, that's cool.
Yeah, so you see mobile devices right here. What are we talking about? 5.6? 5.6, right? Let me see 5.6 gigahertz. So that should be right here. Okay, I think that's what that this is what that black thing is right here. Federal, okay, right here. Non-federal shared. I think that's what they mean right here. So you can see, yeah, I think that's what that black line down here is to show that it's open. Maybe not, because I see it in multiple places. Where's the 2 point something? The 2.4, right? Oh, here's your amateur. Here's your amateur. Yeah. Anyways, just to show you, they have to already kind of divide everything out. It's not the Wild West. You can't just claim one. Oh, really? Okay, so tell me, is there a reason it's stacked? Or is it just telling you there's multiple things? I think it's just telling you there's multiple things that's possible in that. It's not saying like this is a higher
I think, yeah.
power than this. I don't think that's what it is. I think
It's just to show, I think there's like a lot more going on.
Yeah. right, right. So
Like with the light, with amateur, you're like very limited to like local communication. Level two, you can like communicate, I think, at like the state level. And then once you get to level three, which is pretty hard to get, you're like, you can communicate with people around the world. But I know, I think it's with, even with amateur though, you can communicate with the International Space Station. Which is
Yeah.
pretty-
Yeah.
And you can
So-
also like build, like, if you know what you're doing, like, the guy that was teaching the course I was like, or the YouTube videos,
Mm.
he just used a whisk and like, that was his microphone.
Oh, what?
A whisk, like a cooking.
Oh,
Yeah, and he was like, if you know how to like do radio frequencies.
Yeah.
And like, you can literally, he was like, you can just grab stuff
yeah.
and like talk into it.
Oh, yeah. Yeah.
Mine,
Yeah, it's pretty
You
cool.
need a razor blade also.
yeah.
Yeah, as long as it can vibrate, right? That's basically what it is.
Didn't you say in one of the classes that your speaker could be used as a microphone?
Yeah.
Yeah.
Because it has a
Yeah.
vibration.
Right, it's a membrane that just vibrates. Yeah,
It's fine.
yeah. Yeah, exactly. Yeah. Can LEDs take pictures? No. It doesn't work like that in that case. Yeah.
We're gonna find out about that pretty soon.
Yeah.
Okay, so you said like, some of these bands, like, some frequencies that anybody can use them.
Yes.
But does that mean use them in what sense, like to broadcast, or can you listen to those like?
Just whatever you want to do. You want to you can use it for like your walkie-talkies or
Like,
oh,
Mesh four and mesh.
yeah, exactly. So that can listen or that can transmit, whatever you want to do. It's like it's yeah, but you may not be able to interpret the data if it's encrypted or whatever, like yeah, so
See, you just can't transmit on something regulated.
Yeah.
Without.
So,
Yes.
I do hold my restricted radio off.
Huh?
permit. Which is like for emergencies if I'm out on a map. You're not supposed to communicate with manned aircraft, but low flying helicopter.
Yeah.
But I've been told, you probably know this, I've been told you're not supposed to, like for VTX, like you shouldn't actually operate on like race band 8 because the frequency, like you were saying, it's actually bleeding over.
It's bleeding over.
But how much is it bleeding over? Because I've also heard like race band 8 is like the go-to.
Yeah. What is race band 8 frequency? Let me see. So it looks like it's at 5.9 gigahertz. And then what is FCC unlicensed frequency range for 5.8 gigahertz? Let me see. 5.875. And what do we just see here? Oh, okay, that's probably why. Yeah. Yeah.
It doesn't stay in a steady stream, so
Yeah. So, yeah, I guess that could potentially be, well, it says right here,
extension.
unlicensed indoor operations in the lowers part to, I don't know. You might actually know more than me about this because I haven't really looked into the ham radio license stuff. So this is actually news to me. I didn't know that. Maybe that's why people do the race band 8 because it's like less things are on it. Because it like
Okay.
most devices are probably not like, they don't want to like get into that edge. Maybe that's why people say that because it's less crowded. Oh.
Everybody always goes, I want race band 8.
Maybe that's
And I've
why.
been told like you're actually like not supposed to because of this.
Oh, I guess like if you want to be official, then don't do that if you don't want to be in that zone. But yeah. But I guess if you're also just kind of out there, I don't know, like maybe not that big of a deal. Yeah. But that's just kind of like the same thing as like, oh, there's no one out here. I'm gonna go speeding, you know what I mean? Like, yeah, so yeah. All right. Yeah. So now that you know, you can make that judgment call. I'll say that. Yeah. Previously I didn't know. Thanks for ruining it for me. Yeah. Yeah, so I'm just curious then, what is race band 7? 5.88? Oh, that's basically okay still. I mean, like 5.785, but like, yeah, okay. I see. I see. Okay. I mean, it looks like there's some license extension, but that was still 5.9, right?
Yeah.
It's okay, so that's like even beyond that still. Yeah. So I guess officially I say no for the recording. Yeah.
We all do that, right?
Yeah. Yeah. Okay. All right, so here's a visualization right here. You can see 5 gigahertz, higher data rate, smaller coverage area, 2.4, lower frequency, but longer wavelength, and it can have a larger coverage area at the expense of lower data rate. Okay. All right, here is a table. Actually, I just saw one. Maybe, yeah, I like this. Maybe this one's more updated. Okay, because the one I've been using is outdated. Huh. I might copy this. Let me copy this and see if I can use that instead. I will first talk about it. If I don't like it, I'll go back to my other one. Okay. So uh this is specifically focusing on the 5.8-ish frequencies. Okay. So, oh, I like this one better. I like this one better. Okay, so you can see, I don't know, per this chart, it says that FCC's is red band at the very top. You see it says 5.65 to, in this case, it says 5.925. You can see the European limitation is a lot tighter. You see this orange one?
Can't recently.
I guess not. Yeah. It like,
Because I recently switched to E5,
Oh.
and now I'm looking at that, and E5 is 5.885.
yeah.
To explain why I'm still getting a great connection.
Oh, yeah. Yeah, that makes
Now
sense.
I'm on frequency.
Right. But this one we're talking 5.8 gigahertz. This is for VTX primarily. Okay, so all these things right here that we're talking about is for the VTX. Now we have two different categories. We have analog and we have digital. Okay, analog is just going to be like, it's gonna look like a old school CRT TV, like staticky, and it's the reason we still use it is because it's lightweight physically, both in like actual size as weight, but also power consumption, a lot less. And it's also cheaper, but the quality is not as good. All right. Fine if you're just casually racing and you're not actually trying to record what the camera sees, you're just using that for flying. Also low latency. People like it for that. Okay, especially when you're racing, every few milliseconds can really make a difference. So you can just specify, hey, I'm gonna go on, for example, 5,770 5,725 megahertz frequency, or you can use one of these pre-designated allocations. So if we're on A band channel number 8 is going to be the 5,275. It's a lot easier to say I'm on A band 8, and then someone else can be like, okay, I'll be A band 4, rather than call out the specific frequency. So a very common one is race band, or just R right here. And race band, you can see the reason I think it's more Popular is because it's evenly spaced out. You notice there is a curve here, a bell curve, because it's not like this is the target. The target frequency is 5,658, but you'll get a little bleed over just like if you turn the radio on and you go to a specific channel, but then you just turn like 0.2 off, you still hear it. It's just kind of staticky, right? So same thing here. There's a little bit of bleed over. So raceband is nice because you see it's nicely separated to avoid any potential crossover. So you can, we were talking about raceband 8 down here. So you can see right here, that's at 5,917, which I guess per this thing is still okay. But you can see a portion of it does fall off. You see that? A portion of it did fall off. So just, I guess you could say the same about raceband 1. So some of these other ones, they just have a little bit more overlap. The idea is when you're flying with multiple pilots, try to space yourself out, just like you naturally do when you get onto like a bus. You don't just sit next to someone if there's like a bunch of empty chairs, right? You just kind of naturally space out. So you can see this is what this additional chart is showing down here. Let's say you have 4 pilots flying. Well, put yourself on raceband 1, raceband 3, raceband 6, and raceband, well, they said raceband 7. But basically, you see, we're not doing like 1, 2, 3, 4. We're like trying to space it out to avoid any interference. If it's 5, then you can reallocate accordingly. 6, reallocate accordingly. So that's the idea. Try to avoid being right next to each other. Okay, so A, B, E, F, I, R, these ones are all analog. So analog has kind of a bell curve shape. The S, D, J down here, you notice it's a boxy shape. Okay, those are digital signals. They are still using the same frequencies, but they're just sending out the signal differently. All right. So we have a SharkBite DJI system, and yeah, they have their own allocation right here. Okay. And then you can see Wi-Fi also shares this, so things can get kind of crowded. The thing about analog, which is nice, is it's not tied to a specific manufacturer. Okay. So you see digital like DJI, if you want to be able to broadcast and receive DJI signal, you need to buy DJI equipment. Okay. There's other companies like we have the what is it called again? The okay, we're using a HD system. Yeah, the Voxnail. Okay, yeah, we're using that. You can't just look at an DJI system with that. Okay, you even though they're both HD, they're kind of like their own proprietary little thing. Analog, on the other hand, you can buy whatever brand, it doesn't matter because they are just broadcasting strictly frequency. Okay, they're not broadcasting like particular information. Okay, so they're just strictly doing. It's just like you listening to the radio. It doesn't matter what brand car. As long as you have an FM, AM, you can listen to the radio. Okay, so that's what's nice about the analog is that it's not tied to a specific brand. So, but digital, if you guys ever experience, is nice and crisp, right? Like it's like HD, yeah. So there is that. Okay, I like this image better than this one. This one kind of shows the same thing. You can see this is my old one, but I think I'm gonna move away from it now. Oh, I didn't even notice. They did have the SEC and the CE.
You say on this one, you do have HD0 and Voxnail listed.
Yeah, this is nice also, right? Okay, well. Anyways, you can see the colored rows and the boxy ones are the HD, and then the ones that have the bell curve, there's no particular brand associated with these, all right? Whereas these ones do have brands associated with them. They're kind of their own thing. All right. Any questions on this? Yes.
How can we make it into this? I'm sorry if it's early, but
Mm.
if you were doing a project where you were gonna go like map out or fly or race through, let's just say a really dense old abandoned building.
Yeah.
Do you have to consider penetration? Like, if you're trying to fly the drone in the broken sunroof and then you go down,
Yeah.
hey, I'd rather go analog versus digital, will you lose connection or, I mean, at any degree? Cause I know that you said that for racing, it seems like analog is great because of the lack of lag.
Yeah.
In the inverse, is there any, besides it being crisp, is there any functional benefit for digital
For digital,
versus analog, depending on the project?
uh, the main thing I can think of digital is just mainly for the crispness. Do you have a
I think.
Actually, I don't fly FPV that much, so I don't know in this situation which one's better. You fly FPV more, right? Yeah.
For like abandoned building you're talking, do you have the ability to strap a GoPro on? That would be the best bet.
Okay.
So,
Like flying
Yeah.
analog, but filming.
right. That used to be your only option before HD came out. Is like you just fly with the GoPro attached. Actually, you know the drones that we're making, that little white nub on the top is a GoPro mount. It's for that purpose. Yeah.
You, with your VTX, if you got a strong enough one, you can blast through.
Yeah.
And then it comes down to like, if you have true diversity goggles, you want one Omni and then a patch antenna.
Mhm.
And your patch antenna, I would get a strong one. It's very directional, but it can punch through stuff.
Yeah. Yeah. So, but between HD and analog,
I fly analog just because it's cheap. If you
Okay.
break it, it's
Yeah.
like, oh, it's a quick fix. If you bust up your digital camera, there's $300.
something makes me think analog is also better for like penetration than digital. It's also analog will start to degrade like kind of gradually versus digital is like kind of a sudden.
It's either
Yeah.
works or it doesn't.
Yeah, yeah.
Okay.
So you get an idea of when analog is about to go out and you can like decide not to go any
I think a
farther.
lot of people are going back to analog, not just because of price, but because of like understood.
Okay.
Yeah.
Okay.
You get like a drop off versus just like hands out.
I know a lot of it comes down to like what VTX you're running.
Huh.
Cause there's a brand called like Rush Tank or Rush, but they have
Yeah.
the Rush Tank. And it's like the one that says you need a ham radio because you can jack it all the way up.
Oh, cool.
And that's like, I think it's also for like long range.
Okay.
But if you don't have to do a full GoPro either. You can get the naked GoPros, which is basically like completely dismantled GoPro.
Yeah.
And then you just 3D print or you buy a little frame for it, so you don't have the weight dragging you down.
Okay.
Okay, cool.
Well, AI says analog is the preferred choice for flying deep inside buildings. Yeah. And this is what I was talking earlier. The signal grades gradually. Yeah. Digital can just drop. Yeah. Ultra low, that's good if you're like flying fast. Yeah, so what you do is you just bump up your power. It's just like yelling louder. That's like the main thing you can do. What were you gonna say?
Is it possible, like, because you can you can bump up your power all you want, but it's possible to burn those out, isn't it? If it's not rated.
Oh, yeah, I mean,
'Cause I mean,
usually the VTX,
catch theirs on fire and I'm
Oh.
like, you jacked up your power.
Okay.
Like,
but like, are you overriding what the VTX allows or?
well, on your beta flight, you can do a lot.
Oh, okay. Yeah. Well, I mean, yeah, that could be for anything, right? Like if you go beyond what the rated limit is. VTX is the thing that gets, I would say it's the hottest thing on your drum. So later when we start working on it, we need to use our old vents or old like solder fume extractors to keep it cool. Yeah. But yeah, no, these are great questions. I wanted to show something, but now I forgot. But yeah, he mentioned the like antennas, so that'll be things I want to put in that video, like yeah, because that's like the hardware consideration. Like I'm just talking concept right now, but like in the end, when you buy something, you're like, oh, like what do I actually buy? And that can make a big difference in terms of like how far your signal goes. Like you can have a directional or it can be a broad, yeah.
So
So
it goes into what you're saying. I know we're not there yet with the
Mm.
polarization.
yeah, exactly. Yeah.
Like, I made the mistake of buying like the left versus the right. And
Yeah.
Turn.
Right, yeah. So that's the thing. It's like there's so many like got yous when you're like building something. Yeah, there's just so many different parameters to consider. And I'm not talking even like designing from the ground up. I'm just saying like, oh, you want to build something with existing components. Like just what thing, like which filter like drop down do you need to like choose to get to the right thing? There's the physical size, and then there's like frequency. Like for example, you can buy a like so far we only showed right here the VTX, but like same thing for the receiver. You can buy a 2.4 gigahertz receiver, or you can buy a 915 megahertz receiver. And then if you buy that, but your other controller is not the same, it's not going to talk. Yeah, it's got to match. It's got to match frequency and it's got to match protocol too. I'll go over that later too. Protocol is like basically like your language.
We're running 2.4 ELR.
Yeah, we're doing 2.4 ELRS, but I had people buy a 915. And then it's like, well, it's not going to work. It's both ELRS, but it's just like they're talking. Yes, so there's just a lot of things that can potentially go wrong, but thankfully it's a matter of just like buying the right one. It's not like it'll break mid-flight because you won't even get it working to begin with. So that's a good thing. Okay, this is just another table to show you uh analog versus digital and the different frequencies. Okay. Well, I like the ones that show you visually the graph, but I just want to lay it out there. Okay, so oh, I went over basically all this stuff right here. So we looked at the 5.8, which Wi-Fi also shares. Remember, 5.8 is just a generalization. It's really this like bigger range that we saw. Okay, so what do we see right here? Like 5650 all the way to 5925. Okay, so we just kind of say the generalization of 5.8, but realize it's a range. Okay, and we talked about race band for analog at least. It has the largest separations. And you want to assign frequencies as far away as possible when you're flying with other people. Okay. Okay, so I just mentioned protocols, and now we're gonna look at them. So you're gonna hear a lot of these terms, and it can be a little confusing in terms of what they're referring to. So right now, we're just going to look at the controller and the receiver. Okay, that is like a bundle. I talked about it previously, but we're focusing on 2.4 gigahertz. Okay, that is our frequency for controller and receiver. VTX is what? What do we use for VTX? 5.8. Okay, so 2.4 right here. Now, on the controller itself, we have a firmware, and the ones with the thumbs up is my current and recommended. HTX is your firmware. So when you turn on the controller, we will see that pop up on the screen, just like Windows XP, or sorry, I'm dating myself. Windows, whatever now, Windows 10, okay? Yeah. Yeah. I still have that green Bliss Hill scarred in my mind, okay? That's all I just like. First computer I got, yeah, Windows XP. Okay, anyways. But yeah, it's whatever Windows now is. 11? Is that what it is? Okay, so yeah, so that's like the equivalent, okay? Radio link protocol. We have Express LRS. So that is a open source, very popular protocol. Protocol, you can think of it as like a language. So we have different languages. Even though they can use the same frequency, meaning you're speaking at the same rate, but if you have one radio that is for Express LRS and then your receiver is for Crossfire or like, FR Sky, it's not going to talk. You're just not going to understand. So you have to make sure that your radio and your receiver is on the same protocol and the same frequency. Okay, so you can see right here, Express LRS. We had people in the past because our controllers here, we use Express LRS 2.4 gigahertz. But some people bought Express LRS 915 megahertz. It's not going to work. All right, so make sure you get both of those conditions. And then furthermore, even more confusing is this is just a protocol, right? Like all of us can speak English, but we're all different, distinct people, right? So you can buy an Express LRS module from one company, and then you can buy another one, and they'll still work. That's a good thing. All right, that's a good thing. Different brands will make different devices. As long as you make sure you meet those two criteria, Express LRS 2.4 gigahertz, you're going to be okay. All right, so it doesn't matter the brand. This is not a brand, although some of them are tied to brands, okay? So like TBS, I think they're the only ones that can sell their own thing, okay? Team Black Sheep, that's what it stands for, okay? They're like their own little proprietary thing, all right? But Express LRS is open source, so you're going to see a lot of like brands selling Express LRS. Okay. Oh, I'm already starting to talk about, I don't like the order I do this. Let me skip to this slide because I like to show where this comes into play. We have our controller itself, and then the firmware. What did I say earlier about the firmware? What was the recommendation? Anyone remember? Yeah, EdgeTX. Okay, so that's what would show up. That's what lives on this actual device. But then right here, it's talking. What are we using in this class? It's talking wirelessly. Which protocol? That's the frequency. Yes. Express LRS. Okay, so this is what we're looking at right now. We're just looking at the wireless communication. To make it even more confusing, we also have a wired communication now from your, what is this thing? A receiver to your flight control board, you see? And you should have already seen that when you're building your drone, right?
Yeah.
That is not Express LRS anymore. Oh, so it's going to be, okay, so sorry, backtracking. We're talking wireless protocols. These are the recommended ones, although realistically, if you're starting from scratch, I would just go with this. Okay. Now we're talking the receiver protocol is going to be CRSF, and that's going to encompass those other ones I talked about previously. So when I started, this was like super confusing because like there's just so much different terminology out there. Okay, so this receiver protocol is CRSF. That is right here. That's our wired communication right here now. Okay.
Is that why that CRSF, like, so I have the TX12.
Yeah.
And it's EdgeTX ELRS,
Yes.
but when I go in and I turn on my internal radio frequency, it says CRSF.
Oh, that one's probably referring to Crossfire TBS, which is also very confusing. Okay. I think, okay.
It says CRSF and then 250 megahertz.
Yeah.
Communicating with my ELRS.
Yeah. Yeah.
It's like, is that just what you're talking about there with it?
I think so.
Okay.
I think so. Show me. Yeah. Oh, okay. All right. I think so. So what's kind of confusing is TBS being its own little thing. Express LRS, from what I understand, is that they kind of like figured out or reverse engineered TBS thing or something, and they made a branch off of it, and then the wired communication, that's why you can see all of these still fall under CRSF, which I believe stands for Crossfire. I don't know. But there's kind of like some interweaving of some sort. I think maybe there was perhaps I don't know what the entire history is of how this happened. I just know Crossfire or TBS existed first, and then like Express LRS emerged later. Yeah. Yeah. There was some like there's some crossover, and that's why you see a lot of them still like kind of have relationship with each other. Like Express LRS, TBS, Tracer, they all fall under CRSF, which is right here. We're talking receiver protocol. And then finally, to talk to the ESC, we have another protocol. Oh no, I know, another protocol. Okay, these are the different ESC protocols. And the one that we're going to be using is DShot, and they have different versions of it. Okay. We will see this later when we get to the programming and configuration part of the software. So I guess I will probably just stop here because it's also 7:30. Sorry about that. Do you guys need a break? Yes. I need a break too. We will come back. Okay, I'm gonna install the camera now. So the camera to install in the front, we need to have these devices. This is the plate. There's two of them. You're gonna want one of these spacer bars with the knurling pattern on it. And then we want these kind of circular with 3 tabs plastic pieces. What you want to do is assemble it together. The bar across it at the bottom. This is the bottom. And the reason, the way you can tell is you see there's this rectangular slot right here. The rectangular slot, that's going to allow you to put this tab in there, okay? You see, I'm gonna put this like that. Yeah. So what you want to do is you want to have this particular orientation. It's very particular. With our drones, when you're flying them, your drone will naturally pitch down. Your drone's naturally going to pitch down like this as it's going forward. If your camera is normally pointing forward, it's also going to pitch down. And now you're just looking at the ground. So what you want to do is you want to purposely tilt your camera up a little bit. And in order to tilt that, we have these little curved slots. So what you want is, let me take a photo just to show you. That way it's not so shaky. Okay, what you want is, you want the curves like to be tilted this way. That way the camera is gonna look that way. All right, that's the whole point. The camera looks up to compensate for your drone tilting down. And therefore it ends up looking forward. And then you're gonna have a nice long flat slot. So that long flat slot is gonna face forward. So it's gonna be the mirror image on the other side. So this is me showing the, what is it? From the top looking down, it's the right side of the drone, okay? Here, I'll come around and help people just to make sure that you align it correctly. And then once you aligned it, what you want to do is here, let me go over this point, and then I'll come around and help people. What you want to do is you see your camera itself has 2 holes on each side. Okay, that's going to correspond with those curved slots. So I'm gonna line it up like that, you see? And then with the curve slot, it gives me a little bit of degree of tilt. I can tilt one way or the other. Very important. Make sure your camera, the arrow is pointing up. The arrow is right side up. You guys, you can't really see the arrow. Oh, there it is. You see the arrow? That's right side up. Okay, otherwise you're gonna mount your camera upside down and you're gonna have to redo all that. So make sure your camera arrow is up when you install it like this. So what's gonna look like is it's gonna look like this. You see? Camera is squeezed between the plate. And the two screws you're gonna put in is going to be okay, it's gonna be a 2mm M2 lengthwise. Let's take a look here. It's gonna be an M2 by 5, if I had to guess, something like that. M2 by 5. Okay. Remember when we measure the bolts, I say this is the 5mm, and then the diameter is gonna be M2 right here. All right. Let me come around.